I'm standing here, Kasper Moth Poulsen, Assistant Professor at Chalmers University of Technology, the division called Applied Chemistry, and leader of a group trying to solve one of the biggest challenges in this world with limited resources, how to capture and store solar energy. Tell us about this gigantic challenge.
Yes, so in a future society where we have limited resources in terms of fossil fuels, we would like to develop technologies that can where we can harvest, for example, solar energy. And today, photovoltaics, for example, have become tremendously effective and also very price competitive. So today, in some countries, they are implemented on a large scale. But associated with this challenge of producing solar energy is also the problem that the sun doesn't shine at night, or in Nordic countries like Denmark and Sweden, we don't have so much sun in the winter. So associated with implementing large-scale solar energy, there's also a storage of energy that is going to be a future challenge. Because solar energy power production needs to be used directly. We cannot store the energy we have no technology to store the energy from the solar panels. So what we are trying to do is to build a system where we store the solar energy as chemical energy in molecules. We call it molecular solar thermal. And the idea here is that we irradiate a molecule with light, and the molecule is then converted into another molecule that we can store over time. And then, when we need this energy out again, we can trigger this molecule to release the energy that we have stored and heat something. And then we can use this heat to drive to heat a house, or to drive some heating something in a factory, for example, where you need to heat something.
Before we go into the molecule, which is obviously the key in your research, I mean, science group all over the world is trying to solve this big challenge for many decades, actually. Why haven't they succeeded? What is the big problem?
So there's several challenges and several ways you can address this problem. You can imagine if you just could build very large batteries, for example, then you could solve this. But it has been very challenging and very expensive to try to build batteries, and no battery technology that can, for example, fuel a whole city or provide power for a whole city. That is not possible. You can make batteries for cars, but already that is very challenging. On the other hand, there are people trying to do chemical storage in different ways. There's a research area called artificial photosynthesis, where they try to also convert solar energy into chemical energy, or trying to convert water into hydrogen. And that is progressing, but it's very difficult. It's not so easy. It also has to be, not only it has to work and be efficient, it also has to be cost effective. And that is something that might work in the lab might be too expensive to meet the market. So there's many challenges in this. And what we do as scientists is we explore what is possible, and we try to change and explore. Every week we go to work and try to expand what is possible and test. Can we do this or can we do that? Then from a discovery in the lab to a real-world device or real-world application, there's a long road of optimization, market evaluation. I mean, the costs have to come together and so on. So there are many challenges associated with this, and we are in the first step of developing something new. So it's not something that will work tomorrow. It may be something that can work in 10 or 15 years or more. But we are exploring the possible, so to say.
And your sort of bet in this is a synthetic molecule. So tell us, is it a molecule that you create here in the laboratory?
Yeah, so we are basically we are a synthetic chemistry group. So we design molecules and try to improve the properties. And for this molecular solar thermal, there's a lot of properties we need to take care of. For example, the molecule has to absorb the solar light in a very efficient way. It needs to store the solar energy in an efficient way, and needs to be able to release this energy again. And all these steps we need to take into account when we design the molecule, and that we do by thinking, but also by combining our thinking with quantum chemical models, computer models of how this molecule will work. So then when we have a good candidate molecule, then we look into the synthetic chemistry literature and try to combine what is known from the last 150 years of chemistry into a synthetic procedure that we test in the lab. Then we test that. We start from molecules that we can buy. Maybe it comes from oil, maybe it comes from plants. We convert it in several synthetic steps, and in the end we stand with the molecule we have designed, and then we can test the properties of this molecule. And hopefully it's better than the previous generation. So ideally we should be able to improve and improve until we get something that is really effective.
A molecule is obviously very, very small, and it's quite abstract how it works. How would you see your final product, so to speak? Is it a liquid like water to transport?
Yeah, so ideally the molecule should be a liquid like water, or like some fluid that we can pump into a solar collector, and then where it stores the energy, and then it could be pumped down in a storage tank where it's saved there for future use. And then when we need the energy, we can pump it back into some energy release device that consists of a catalyst maybe, and there we release the energy and use that energy when we need it, and then we can reuse the molecule. So it's a really closed cycle, zero emission project. I mean, there's no combustion, there's no release of any chemicals or anything to the outside world. It's a closed cycle. We reuse the same compound again and again and again.
So is this pretty much how you try to use water to heat, except that it doesn't lose the heat on its way?
Exactly. So I mean, one of the existing technologies that do sort of the same is you could heat water and store it in a large bath of water that maybe is 50 degrees or 60 degrees warm, and then reuse this temperature, this heated water later. But the challenge with this is you need to isolate the water not to lose the energy, and also the temperature gradient. I mean, you cannot heat more than 60 degrees or 80 degrees with this water. It cannot be warmer than that. So we hope to reach higher energy density so that we can heat something several hundred degrees.
Okay.
So that is our niche, is that we can store our molecules for years, and then we can potentially reach higher temperature gradients. That is our goal. We want to be able to heat something several hundred degrees with this stored chemical energy.
Can you make electricity from this?
You can. It is a possibility. The challenge of converting heat into electricity is governed by classical thermodynamics, and there's a limit to how efficient this could be. So typically when you have low temperature gradients that we will have in our systems, the efficiency can maximally become 10-15% probably. And this is one possibility, to use it as a way to store energy and then convert it into heat and then into electricity and use the electricity. I think the first application for us could be more in areas where you need heat on demand, for example in industrial processes that need heating, or to house heating and so on. But that is the future to tell. I mean, we do basic research, we try to develop the processes and the molecules and see how efficient they can be. Once we reach that state where we really think we have some really efficient, then we can try to see what is the market. But
and we're actually standing here in the lab where you do these synthetic molecules and try to, and we have very strong light here. What are you doing here?
Yeah, I have here a picture of how our setup could be. We have a solar collector here, and then the storage tank I mentioned, and then the heat release part. And here we have an example of one way how this solar collector part could be. And we are standing here with a test device that we are building. And to test it, we have a special lamp that has a solar spectrum equal to the solar spectrum. So this is
that equals the sun.
Yeah. So this is our equivalent to the sun, because some days it's a shade in Gothenburg, so we cannot have full power. So we use this solar simulator, and then here is our device that consists of what is called a solar concentrator, which is basically a mirror.
Okay.
And then we have a transparent glass tube where we pump the molecules through. So this concentrator mirror changes the position of takes all this sun that hits this and focus it into this very narrow channel. And by that we get a very high intensity light, and that means that we think this is a sort of economic way to build devices like this. So we can pump our molecules through and photo convert them inside this small channel here.
Okay.
So this is what we do.
And what you mentioned year here, 10 to 15 years before you can see. What kind of breakthroughs do you still have to make in order to make ready products, so
Yeah,
to
yeah.
speak.
So last year we demonstrated the first example of this full cycle reaction, but it was really, really inefficient. It was a fraction of a percent efficient, and it was not really robust enough to work for years and years.
What was the problem?
So there's problems is stability for one. It has to be stable, it has to be more efficient, and it has to be economically viable. So these three major challenges we have to work on this. And right now we are really trying to address the efficiency by improving different aspects of the chemical design of the molecules, and also the economic side, because in our first demonstration we used some very, very expensive chemicals that would not be practical in real world applications. So now we try to use carbon-based materials that you can in principle get from sustainable sources like corn products, and then we could try to convert that into functional molecules. So the goal is to be able to synthesize these type of compounds from completely renewable feedstocks, like the different kind of organic sources. So we're not relying on oil in our synthetic procedures.
Okay. But you have a plan how to do all this?
Yeah, this is our plan.
And you're quite sure that you're going to succeed as well?
We hope, but you never know. It's research. So we are exploring the possible. We don't know if it's going to work, but we try our best, and we have made plans of how to make it work.
And what about the rest of the science world? Do they follow what you're doing here closely? Has it made a lot of international attention?
Yeah. Yes. So when we made this this new discovery last year, there was a lot of interest, and I can see now that other research groups around the world are receiving major funding to sort of follow in our footsteps and do similar things. So it's really creating a lot of attention, and also we've been in contact with other scientists who want to do similar things than this. So it's really.
And what are your commercial? Not commercial. Wrong. What is your actually edge? What are your uniqueness in order to be ahead of all the other science groups?
Yeah. So
it's the molecule that is a key here.
So the challenge is, I mean, we started this because we wanted to see if it's possible, and so when we started this, there was not so many other people doing it. It is a research area that have seen some activity back in the 70s and 80s, but then it has been quite silent. And we thought we wanted to research this again and do new things in this area. So when we started this, we were more alone in the world, maybe not so much competition, but now there will be competitors, and then we really have to step up and be sure that we are ahead of competition. So I mean, we try to do our best and be good synthetic chemists to develop new molecules as fast as we can, but it's also a funding issue, of course. If we have the sufficient manpower, then we will stay ahead. If not, then it will be challenging to keep up with the competition.
And to solve the world's energy challenge is also obviously a great commercial challenge from the commercial world. What can you say about the interest from companies around your research?
Yeah, there are some companies that have shown interest in this, and also, so there are some companies that have shown interest in this. Personally, I think we need to prove ourselves a little bit more. I think we need to improve the efficiency a little bit more, so we are closer to the application. So I think we will need 3, 4, 5 years more of basic research before we can start to do the first demonstration, closer to commercial demonstration devices. Because there is some challenges with stability and efficiency that has to be solved first before it's meaningful to think about applications. And as a basic research university, this is our job. I mean, we need to test if it's possible or not, and we try to do things that the companies cannot do, or that is too high risk for the companies. So we should do our best to do this research, and then at some point it should be ready for the companies to take over. And so I try to keep a dialogue with these companies and discuss what are their needs, what kind of applications could they be looking at, and how should we try to design our experiments so they are as relevant as possible. But I think it will take some years, and I think it's also important to be honest about this, that we're doing basic research with an applied application in mind. So
you were mentioning this was a big research field in the 70s. What do one know today in order to pick up this kind of research?
Yes. So today there has been impressive progress in many areas of chemistry and computational methods in particular. So I think today, with the help of computational methods to design these molecules, I think we have a better possibility to design the molecule and also understand the processes and how they work. And if we understand how they work, we can also have a better possibility to improve the performance of these type of materials. So this is what I think. I think we have a better edge we can move faster than they could back then because of the help of computer technology of different ways, different kinds, and progress in computational methods in particular. Okay. Computational.
Computational.
The use of computers.
Oh, okay.
Yeah.
Okay.
Yeah. So you can model the properties of molecules or model the energies in molecules in a computer. And if you can do that in an efficient way, then you don't have to go into the lab and build the whole molecule atom by atom. And then you can, if you have a good model, you can screen hundreds of different candidates and choose the top candidates that you can go into the lab and make. And that is a way to save time and make more advanced molecules and better progress, I think.
Finally, your personal thought, is this going to be an important building stone for solving the energy challenge in the world when it comes to solar energy? I think
not one technology can solve everything, and I think our niche is going to be areas where heating is needed, like industrial processes where low to medium temperature heating is needed. It's about 16% of energy consumption in industry in the world, and maybe for house heating also it could be a part, but we are not going to solve all energy issues with this technology. It's going to be add-on or be competitive in certain niches. I don't think one single technology. I mean, solar energy is one, wind, hydropower, and others will be the combination of this will be the future energy mix, I think.